Good evening, folks. How y'all doing? This is Mike with another video on Foundations of Mathematics 2. In our previous video, we talked about calculating simple interest and some related concepts to it, the banker's rule as well as discounted loans. And we left off with a little teaser of how we're going to compare simple interest to compound interest and see how we get more interest if we calculate it using compound interest and the formulas associated with that. But first thing we need to do before we talk about the compound interest is we want to actually do a sample problem and compare. So before we get to the general compound interest formula, as I said, let's do a sample problem and compare. So here's the situation. You deposit $9,000 into a savings account that has an annual interest rate of 5%. First, we're going to calculate the simple interest, and then we're going to calculate the compound interest. It's compounded annually if the money sits in there for 2 years. And think back to the end of our previous video. We said that simple interest is interest calculated based on what you put in at the very beginning. With compound interest, interest is determined based on your balance at the end of the previous time period. In this case, at the end of the first year / very beginning of your second year. So let's calculate the simple interest first. Simple interest, we have our formula I equals PRT, principal times rate times time. Principal is 9,000, the rate of 5% or 0.05 times the time of 2 years. And 9,000 times 0.05 times 2 is equal to 900. Very easy to plug that into your calculator and figure that out. So that's the total amount of interest that we're getting for those 2 years. With compound interest, what we have to do is we actually have to do 2 separate calculations. I have to calculate the interest that I get for the first year, figure out what my balance will be at the end of that first year, and then calculate the interest for my second year, and the principal that I'm going to use will be what my balance was at the end of that first year. So with compound, I'll label it year 1. The interest I'm going to get is going to equal 9,000 times 0.05 times 1. Or if you do 9,000 times 0.05 times 1, and this is going to give you $450. And that means that my balance is going to be $9,450. Now, for year 2, I'm going to essentially use a very similar formula just to calculate the interest. But now my principal is going to be this 9,450, not the 9,000 that we had at the very start. So 9,450 times 0.05 times 1. And this is a little bit nastier of a calculation. So if you do 9,450 times 0.05 in your calculator, you are going to get $472.50. And if I add this interest up, it's going to be $922.50. So we can see with just simple interest, we're only getting $900. With compounded interest, we're getting $922.50. So a little bit more with our compound interest there. Very nice. And we'd find that there'd be even a greater difference between these two quantities of interest if I kept this going on for more and more years. 5, 10, 20. We get significantly more interest using compound interest versus the simple interest. So really we're using the same formula in some sense to calculate compound versus simple interest, but what we're using in the formula for compound, the values aren't always exactly the same for each time period. And also we did this where the interest was compounded once per year. That's not necessarily the case. So the following formula, which is going to give us the future value of a savings account with compound interest, this is the formula that we use a lot more often. This is what you'll see problems on. This right here, this was just a nice little sample just to show you, oh yeah, we do get more interest when we use compound interest versus simple. So in this problem that we just did, we said interest was compounded once per year. We could easily compound interest more than once per year though. Most banks, when they calculate interest on your savings, it's very common to do it every 6 months, so semi-annually, quarterly, monthly. Some places may even do daily. I highly doubt it though, but probably the two most common that banks will do is either monthly or quarterly. Obviously, if it's monthly, we're compounding or calculating interest 12 times per year. If it's quarterly, we are compounding interest 4 times per year. So if we deposit P dollars into an account that has an annual interest rate R, and again, we're using R as a decimal here, not as a percentage, as a decimal, and we're going to compound interest N times per year, then our balance, which we let be represented by capital A, our balance after T years is going to be given by this formula right here. It's going to be P times the quantity 1 plus R over N. And that 1 plus R over N is raised to the power N times T. Now, I want it to be very clear, this exponent of N times T only applies to this here. It does not apply to that P. This exponent here, this only applies to the 1 plus R over N. So when you do this calculation, you have to figure out what this is, and you have to take this number, this 1 plus R over N, and you have to raise it to this power. When you raise this to that power, you'll get some number. You then take that number and you multiply it by P, and that is what gives you your balance. And we'll see this in the sample problem that we are just about to do, but the more often you compound interest per year, you'll actually get a little bit more interest. Not a significant difference, but the more often you compound, the more interest you get, and thus the larger your balance is going to be. So we're going to see how this works out with this sample problem here. We are going to deposit $12,000 into an account with annual interest rate of 4%, and it's going to sit there for 3 years. We're going to find the balance of this account after those 3 years if interest is compounded annually, quarterly, and daily. So we're going to set each of these things up first. And then after we get all the formulas set up, then we'll actually do the calculations and we'll see what they come out to be. So again, a quick recap for what these things are. P is the amount of money that we deposit to start with. We deposited $12,000. So kicking it off with 12,000 times, it's now 1 plus my interest rate, R, use as a decimal, so not 4, but 0.04, divided by the number of times we compound per year, 1, times, or sorry, raised to the power of the number of times we compound, N, times the number of years, 3. So we get 12,000. Obviously, 0.04 divided by 1 is just 0.04. 1 plus 0.04 is 1.04. And then 1 times 3 is 3. All right, quarterly. A, we still have the same principal value. We still have 12,000 times 1 plus my interest rate as a decimal, divided by the number of times I compound per year. Here we're doing it quarterly, so quarter, 4 times per year, raised to the power of N, 4 times T, 3. 0.04 divided by 4 is 0.01. 1 plus 0.01 is 1.01. And this is going to be raised to the 12th power. 4 times 3 gives me 12. And now daily, A, again, 12,000. 1 plus, again, my annual rate. But now we are doing daily here. Let's use our banker's rule. Again, it doesn't typically work out in our favor, but what the heck, that is very likely how banks and other financial institutions actually do calculate interest. So let's go with the banker's rule. We'll use 360. And then raised to the power, N, times T, 3 years. Now, we get 12,000 times. That 0.04 divided by 360 is not the prettiest looking thing, but if we write it as a decimal, we get 0.000111111 going on, so on and so forth. So 1.0001, say, raised to the power of 360 times 3 is going to be 1,080. So these are our 3 exponential quantities here. Now we just have to calculate each of them. If you do 1.04 to the cube power, you get 1.124864. Multiply that by 12,000 and round to 2 decimal places. You get $13,498.37. Okay, that's our first one there. Second one if I do 1.01 raised to the 12th power, that's going to give me 1.1268 and then some numbers after that. Multiply that by 12,000. We get $13,521.90. So we can already see a little bit more. As I said, not a lot more, but it is a little bit more. And now our third one here, 1.0001 raised to the power of 1,080. Multiply that by, take that number and multiply it by 12,000. And when you multiply it by 12,000, you get $13,529.71. And actually, the way you get that value is actually by adding more ones onto the end here. You actually have to do 1.0001111. And if you kept adding more ones onto the end, you'd see a very small increase in that value here. So having those extra places to the right of your decimal involved in your calculation can become very important when we get to things like this. But you can see we are getting a little bit larger as we go, as we compound more often. We are getting a little bit more money. As I said, not that much, but hey, every extra dollar helps, every extra buck counts. So this is one sample problem, but a few separate uses of our formula for the future value of a savings account when interest is compounded. Or we use compounded interest, not simple. So because there is that difference in the amount of interest that we get using compound interest versus simple, we have a term for the interest rate that if we use this interest rate for simple interest, it would give us the same interest rate, or sorry, it would give us the same amount of interest as the stated rate did for when we used compound interest. And the term for this special interest rate is called the effective interest rate. The given rate that's stated to you in the contract for the investment or in setting up the savings account, that given rate is known as the nominal rate of interest. And we have a formula that we can use to figure out the effective interest rate. It's only based on the nominal rate, R, and then the number of times you compound per year. The effective interest rate, E, is 1 plus R over N. That whole thing raised to the nth power, and then that number minus 1. So here's a sample problem where we find the effective interest rate. We're going to find the effective interest rate if the given rate, or nominal rate as we said, is 5% and interest is compounded monthly. So R as a decimal is 0.05. N, the number of times we're compounding per year. Well, interest is compounded monthly, so 12 months in a year. N is going to equal 12. So the effective interest rate, 1 plus my R value over N, 0.05 over 12, raised to the 12th minus 1. If you do 0.05 divided by 12, and then add 1 onto that result, you get, rounding to several decimal places here, 1.00416667 approximately. And we're going to raise that to the 12th. 416667 raised to the 12th. We're going to get, when we just do this calculation here, we're going to get 1.05116, somewhere very close to that. The full list of numbers that I can see on my calculator is as such. And then I still have that minus 1. And that's going to leave 0.05116194. Now this is the effective interest rate as a decimal. To convert it to percentage, as we know, take that decimal point, move it 2 places to the right, and tack on the percentage sign. So the effective interest rate is approximately 5.116%. Typically, when we're talking about interest rates, we wouldn't even go this many decimal places out to the right. Typically, we'd only go 1, and we just say it's about 5.1%. But you can see a little bit larger, tiny bit larger, not that much, but there is a difference between that effective interest rate and the nominal rate. And the last thing I want to mention and just show you a formula on is about a special type of savings investment plan known as an annuity. An annuity is a savings investment plan where you make a regular fixed payment into a compound interest account where the interest rate for this account doesn't change over the term of this plan. If you're going to make a regular fixed monthly payment or just however often you make payments, typically it's monthly, but you know that can vary based on what you set up. If you pay R dollars every time you make a payment into this, and you do that N times per year, so again, it could be monthly, could be quarterly, could be semi-annually, whatever. But R dollars goes in each time for N times per year. And if the account has annual interest rate R, again used as a decimal, then the future value A of this annuity after T years is going to be given by this formula right here. Capital R times the quantity, 1 plus R over N, that raised it to the power NT, minus 1, and then that all over little r over n. So a lot of stuff happening there. But each of these pieces, capital R, little r, n, t, those things would be given to you within the a problem, or those things would be known, and you could calculate what the future value of this thing is going to be after T years. So guys, that concludes this video on compound interest and how it relates to simple interest. 2 big things you should know how to do as a result of this video is you should be able to calculate the future value of a savings account using compound interest, and you should be able to find the effective rate of interest. If you have any questions or comments, please be sure to reach out to me, guys. Emails, texts, voicemails, messages on blimps, drawings in the sand, hieroglyphics, whatever you have to do. Otherwise, until the next video, take it easy.